and I'm here today to talk about the changes relating ISO 14119. And this is relevant because they have just released a new standard, and today we're here to discuss the changes and what's relevant. Just trying to... Okay, so if you have any questions, please put them in the chat, and we will try to answer all of them after the presentation. And if there is not enough time, I will try to answer them on mail or via chat later. So first, I will tell you about what the standard is about. It's a machine safety standard, and it is about interlocking devices associated with guards, and more particular about principles for design and selection. And this is for all energy sources, just a general standard. To give you some scope where the standard relates to other standards, it's a type B standard. So we have three categories of standards. The first one is type A, and this gives basic safety principles and principles for design. The second is type B standards. This gives general principles, for example, safety distances or interlocking guards. And this standard is a type B standard. Then we also have type C standards, and these standards deal with detailed requirements for specific machine groups, for example, conveyors or palletizers. And if a type C standard would deviate from the things I've just said about the type B standard, then those take precedence over the type B standard. Now, we will try using interlocking guards to reduce the risk of machinery. And therefore, I have to explain the correlation with the three-step method. When we will try to reduce a risk relating to a machine, we will always follow the three-step method. So first, we will try using an inherently safe design measure. And in this stage, we're gonna try to take the risk away. For example, if we have angular parts, we can round them so the hazard is removed. But this is not always possible. So if there is a residual risk, we can use safeguarding. And this can be used, for example, when putting a guard around the machine with an interlock to detect presence of persons. If those two steps aren't possible or aren't enough, we can resign to the third step in the three-step method, and this is information for use. And then we will put the hazard in the manual or provide markings on the machine, but this is the last resort. And this standard helps with the second step, safeguarding. So now first I'm going to talk about some structural changes relating the standard. So on the left side you can see the old standard from 2013, and on the right side you see the new standard in red from 2024. The old standard is still the harmonized one. And the new standard is not yet harmonized, but in the future we expect it to be harmonized. The page count increased a little bit in this standard from 68 to 106 pages. And then there are some structural changes relating what is discussed and what not. So first, trapped key systems were in the previous standard not fully discussed, but they were discussed in another technical specification, but they were not fully in the scope of the standard. And now they are fully in the scope of ISO 14119 and included in an annex or specific requirements. Also, in the past, there was a separate technical recommendation, the 24119, and this was used to check the diagnostic coverage or the fault masking of series connection of interlocking devices, and this is now also included in the standards, hence the page increase, and also test procedures are included now. So if we're talking about interlocking devices, in the previous standard, there were 4 types of interlocking devices, and they were divided first into mechanical and non-contact interlocking devices, and then further into coded or uncoded and coded. And this gave us 4 interlocking devices, 4 types of interlocking devices. The first one being mechanical uncoded, second mechanical coded, the third non-contact uncoded, and the fourth non-contact coded. When I talk about non-contact, you can imagine an inductive, magnetic, capacitive, ultrasonic, or optic proximity switch. And a coded is means that the actuator is specifically designed to actuate a certain position switch. Now, in the new standard, now you can see the red meaning the new standard. There is a 5th type of interlocking device introduced, and maybe you've guessed it, but these are the trapped key systems. So now, from now on, we have 5 types of interlocking devices. To give you some feeling with the types of interlocking devices, I will provide some examples. The first type is mechanical uncoded, and a basic example of this is just a position switch. When the roller is pressed inwards, the guard is detected. The second type has to be coded, so the actuator of the interlocking device has to have a certain shape, and here it is a tongue actuator. We will put the tongue on the guard, and then only this can actuate the interlocking device. For the third type of interlocking devices, a basic example of this is a proximity switch or read contacts. In the picture, it's a magnetical proximity switch. And this is uncoded. Why? Because if we use another magnet and bring it near the sensor, the guard will still be detected. The fourth type has to be coded, and an example of this is an interlocking device with RFID. So only certain RFID codes can be detected. And then for the 5th type of interlocking devices, you can see here an example of a trapped key system, but I will go further into detail about the trapped key systems. And therefore, I will use a basic example. So in this example, you can see on the left side a key-operated switch. And on the right side, you see an access lock. Now, if we want to access a hazardous part of the machine, we first have to operate the key switch, and this will seize the hazardous movement in this basic example. Then we have to remove the key and bring it to the access lock, put it in the slot of the access lock. And this gives us the possibility to unlock the guard. And this is just the most basic example, but there are a lot of more possibilities with trapped key systems. Now, when do we use these trapped key systems? There are some use cases that are where it is certainly handy. So the first one is that there is no cabling required. This means that if you have a very long machine or a long line, and you have to add an interlocking device, that a trapped key system can be useful. And secondly, we can use it for harsh environments. For example, if in your environment there are rats that destroy the cabling to the interlocking device, a trapped key system can help you with that. And another use case we once had was a concrete factory, and the process destroyed all the insulation of the cabling. So interlocking device, type 5 interlocking devices were the only possibility here. The standard also says that key transfer plan shall be designed for each trapped key interlocking system. And here on the right, you see an example of this key transfer plan. And it is basically just a drawing, scheme, or diagram depicting the system and sequence of operation. So, for example, first we release the key-operated switch. We transfer it to the slot, and this releases another key. With this key, if we bring it to the key exchange device, we can release 3 keys. And these three keys give us access to the hazard zone. Then if we want to start the machine again, the 3 keys have to be inserted again in the key exchange device. This releases this key, and we bring it back to the key operated switch. And so we can start the machine all over again. Now, the standard also talks a lot about measures to minimize defeat for interlocking devices, because experience has shown that this happens a lot, that interlocking devices are defeated. So in the standard, there is in an annex a table, and this you can use to evaluate if there is a motivation of defeat. And for example, I will not talk about everything in the table, but if it is faster to operate a machine when the interlocking device is defeated or isn't used, then there is a possibility of defeat. The standard gives a procedure to minimize defeat, and therefore the first thing that we will do is implement basic measures, and I will talk about these basic measures in the next slide. Then we will check if there is a motivation to defeat, and we will use the previous annex for this. The third one, and a very important one, I think personally, is check whether the motivation can be eliminated. And this can be done by design measures. For example, we can also choose an appropriate operating mode, for example, maintenance mode. This gives other possibilities to the maintenance personnel, and then there is less motivation of defeat. And also for each type of interlocking devices, there are additional measures to be implemented. But first, some basic measures to minimize defeat. Fasteners of position switches require a tool for loosening. This is pretty obvious that you just can't replace the actuator or remove it. But it's also possible that permanent fixing is required. For example, with the tongue actuator on the right, it is possible that they remove the tongue and put it permanently into the interlocking device, and this would create hazardous machine operations. Also, self-loosening must be prevented. For example, on machines where vibrations are commonplace. And then we will try to put the interlocking devices in difficult to reach positions or hide them. That is shown on the picture on the right. I also told you about additional measures for each type of interlocking device. And there's a table in the standard that gives the requirements for each type of interlocking device in the table. The R stands for recommended. The X stands for one of these measures have to be implemented, but not all of them. And the M stands for mandatory, so this measure must be implemented. Now, this table changed a little bit. in the new standard, and I marked in red the things that changed. Some things became recommended, and also obvious type 5 interlocking devices also have their own recommendations now for measures to defeat. For example, if we have a type 3 interlocking device, it's recommended to perform additional plausibility checks, or one of these measures has to be implemented. For example, mounting out of reach can be done. But now it's no longer a possibility to be compliant with the standard when using non-detachable fixing of interlocking device of the actuator as the only possibility of the X marked space. So these additional measures have to be regarded after choosing your type of interlocking device. Next, I will talk about guard locking. So what is guard locking? We will try to lock the guard itself so that it's impossible to enter the zone. And when is this required? When the system response time is larger than the access time. For example, if I open a door and I walk to a conveyor, and this takes 2 seconds, but it takes the system 10 seconds to stop the hazardous movement, then guard locking is required. Then, for example, the guard is closed until the 10 seconds have passed, and then I can enter the zone. There are different types of guard locking. The first one is guard locking by forum, and this has 3 subcategories. The first one is the locking element is spring applied and power to unlock. In the picture on the right, you can see the principle of this. So a spring pushes the locking element into the guard, and we need power to open the guard. The second is power to lock, power to unlock. And in this principle, we have to first provide power to lock the mechanism, and then if power is, in this example, on the other side provided, we can unlock the guard. In this example, you can imagine a pneumatic cylinder. Then the third type is power to lock, spring to unlock. So to close the guard, we have to provide power. So if the power is cut, the guard is opened. This is the power to lock, spring to unlock mechanism. But it's also possible to use electromagnetic force. And here there's only one type, and I've made a small error in the PDF versions I sent you. So it is only one type of guard locking, and this operates like power unapplied. So when we provide power, the guard is locked, and when we release the power, the guard is unlocked. Then there's a bit of a weird one left, and this is the manually operated delay device. So what is the principle of this? We will, for example, have a lock, and then we have to turn a screw to unlock the guard. And this is very reliable through simplicity. And the time it takes for the screw to unlock the guard is sufficiently to stop the hazardous movement. For example, if it takes me 8 seconds to open the guard with a screw, and it takes me 2 seconds to walk to the conveyor, and the system response time is the hazardous movement is stopped after 10 seconds, this can be used, but it's only appropriate for applications with very low frequency, for example, more than a year. So not for daily used guards. Now, guards can be used for either protection of persons or protection of process. Protection of process is used, for example, if stopping the machine destroys the product. And protection of persons is to protect the operators of the machine. Only the first 2 types, spring applied power to unlock and power to lock, power to unlock, devices can be used for protection of persons. Overall, we call these the power to unlock devices, and only these ones can be used for the protection of persons. Protection of process can be done by the previous two guards, but also by power to lock, spring to unlock, or power on applied, power off released. Be sure to check your own slides because the small error made here. Next, I will talk a little bit about guard locking monitoring because it is necessary to know if the guard is effectively locked. And there we can use two methods. Either we can use monitoring of the locking element, and the locking element can only be engaged when the guard is closed. That's visible on the upper right corner. Or we do the monitoring of the locking element and additionally monitoring of the guard position. When we use electromagnetic force to perform guard locking, then we also have to measure the effective locking force. And in the new standard, it's also said that the subsystem detecting the breaking of the locking means shall have at least a performance level C or SIL 1. Now, when we use guard locking, it can be necessary to implement supplementary releases of guards. And there are three types of supplementary releases. The first one is an escape release, seen in the picture. For example, if there is a hazard that a person gets trapped inside of the hazardous machine, an escape release has to be provided so that they can escape from the hazard zone. Secondly, an emergency release, and this is used from outside of the guards, so not inside the guards, but outside. And this is for emergency situations where access is required to the machine. For example, when there is a fire in the machine and the fire team has to eliminate the fire, this can be used. And third, an auxiliary release. And this is an alternative way for opening the guard when malfunction happens or something like that. But in this picture, you see the auxiliary release is by a screw. We don't like it that much because if an operator has a screw, can open it with a simple tool, safety isn't achieved. Something new in the new standard that was not in the previous standard is interlock blocking. But most of you will already know this because in the right picture, this is a picture from ATEX. And this is used for prevention of unexpected startup. For example, when you open the guard, a mechanical mechanism falls and a padlock can be provided, so nobody can close the guard again. This is neither a part of an interlocking device nor a safety function, but it can be very useful in a lot of machines. I will talk about the series connection of interlocking devices. As mentioned, this is now included in the standard. And I will try to explain to you guys why this is necessary for interlocking devices or why it has to be discussed. Just my presentation wants to work. Yeah, okay. So series connection of interlocking devices. But this is only relevant for interlocking devices with potential free contacts. So no OSSD outputs, only potential free contacts. And this annex gives a guide to estimate the probability of fault masking and the maximum achievable diagnostic coverage with a series connection of interlocking devices. And why is this relevant for interlocking devices associated with guards? Because with guards, it's foreseeable that two guards will be open at the same time. Now, there are two types of fault masking that can go on. The first one is direct fault masking. And this is opening and closing a faulty interlocking guard while another non-faulty interlocking guard is open. This is direct fault masking. And then we have unintended reset of a fault. And this is after a fault in cabling is detected, another door is opened and closed, and the fault is reset. But I will give an animation to explain both types. So first I will do the animation of direct fault masking. So here we're gonna open and close a faulty interlocking guard while another non-faulty interlocking guard is open. So for example, I open interlocking guard B. Both contacts are opened and the logic unit sees that the guard is open. Then I open another door A or guard A. But as you can see, one of the contacts remains stuck. So normally the logic unit would see a fault, but it can't because interlock guard B is open. If we close A again, the logic unit hasn't seen anything. And if we then close B again, no fault is detected. Now, if this happens a lot, or if you have bad luck, and when you open guard A and the other contact is destroyed or stuck, or it doesn't work as foreseen, we can open guard A without the logic unit seeing a fault. So this is direct fault masking because we opened a non-faulty interlocking guard while we opened and closed a faulty interlocking guard. The second one is unintended reset of a fault. And this happens after a fault in the cabling is detected, another door is opened and closed, and therefore the fault can be resetted. So in this example, we open guard A, and again, the same contact is welded or doesn't work, and the logic unit sees a fault. If we close the guard again, the fault remains, and we can't reset because for the logic unit to reset, both channels have to be closed at the same time. But if we now open guard B and close it again, both channels have opened and closed, and we can reset the fault without the logic unit. We can do this, and the logic unit doesn't know that it's for guard A. And why is this one especially important? Imagine you have a hazardous machine and two doors are close to each other. The operator opens the first door, closes it, tries to reset, but it is not possible, and he doesn't find the fault. Then he can open another guard and close it by accident or unknowingness, and then the fault can be resetted, and therefore we can see that there happened a fault in guard A. Now, why is this important? Because the annex gives a table that can be used to determine the maximum achievable diagnostic coverage. For example, if we have one frequently used guard and 2 to 4 non-frequently used guards, the maximum achievable diagnostic coverage is medium. Now, you can think why diagnostic coverage is important. Well, diagnostic coverage is used to determine the performance level. For example, if we need a performance level E, we have a category 4, and diagnostic coverage has to be high, and this is not possible when we are Siri connecting interlocking devices. So that is why it's important. But again, this is only for potential free contacts and not for example, OSSD outputs.